Linear regression is a very important machine learning technique. Before trying any other machine learning technique, I always recommend to use linear regression and look at its predictive power. However, linear regression is not free of its flaws, especially when the number of features is very high as compared to the number of data points. Linear regression can fail. This is where a different class of regression called penalized regression can help. Hi, I am Sachin from Accelerate AI, and in this video I am going to talk about penalized regression. So let me go ahead and share my screen. So in this video we'll talk about some of the challenges with linear regressions. Then we'll talk about what is called as the regularization technique. We'll see what that means. And then we'll specifically talk about three different regularization techniques: Reg, Lasso, and ElasticNet. There are many other different types of regularization techniques like grouped reg and Bayesian regressions and so on, but we'll not cover those in this particular video. So in ridge regression, we'll look at how the cost function changes when we add this regularization. We'll see how to do the parameter estimation. We also have to do the shrinkage estimation, a factor that is added in the cost function. All of these techniques try to make a trade-off between bias and variance. So we'll look at those and then we'll talk about some of the advantages of ridge regression. Similar things we'll do for Lasso and ElasticNet. And at the very end, I'll do a demo in Python on all of these three techniques. And at the very end, I'll share some of the references for those who want to read further about some of these topics. So linear regression, as we know, is a technique in which we try to fit a hyperplane on the given sample data set in such a way that we want to reduce the squared sum of errors or the residuals. Now, linear regression is a very powerful technique and it's widely deployed algorithm. The ordinary least square estimates of the betas from the sample are also what are known as best linear unbiased estimates, even for the population. Linear regression is quick in computation because we have a formula, so we don't have to go and look at the data all the time. And hence it can be used for fairly large data sets as well. The estimates are very interpretable. The model is very interpretable. The coefficients have a nice interpretation. Also, we don't need to do any kind of feature scaling in case of linear regression. And there are no hyperparameters to be tuned in linear regression. So these are good advantages of linear regression. However, there are a few disadvantages as well. The very first being that linear regression makes some of the very strict assumptions around the data distribution itself or error distribution in particular. That the error has to be normally distributed with the mean 0. Also, there should be no heteroscedasticity in the data set. We also cannot have any kind of control on the complexity of the model. In linear regression, the only goal is to reduce the root mean squared error using a hyperplane. So in this case, it is prone to both overfitting when we have too many features and underfitting as well when our data points are large but we do not have too many features. Also, given a lot of features or independent variables, feature selection becomes very time consuming, because if you have to look at all the different combinations of features and then uh, create one model out of it and then test it on the test data set, it becomes very difficult. Now we can skip that exercise and do a stepwise regression, but in stepwise regression there is no guarantee that the best model will be selected by the stepwise method. And very important thing is, when our number of features given by P approaches near to the number of data sets, then the coefficients will have very high variance. And in cases where the number of features is greater than the number of data points, also known as an ill-posed problem, linear or ordinary least square regression will give no solution. In fact, it has multiple solutions, but it will not give us any of the coefficients. So these are some of the disadvantages of ordinary least square linear regression. Now, how do we get past this? So one of the methods is regularization or shrinkage. In this alternative method, we want to fit a model using all of the predictors. However, what we want to do is we put a constraint or regularize the coefficient estimates. So shrinking the coefficient estimates helps us in three ways. It significantly reduces the variance, it helps in feature selection, and it also provides a solution when the number of features are larger than the number of data points themselves. That's quite powerful. So regularization is one of the very first weapons of combating overfitting as well. It tries to constrain the machine learning algorithm and improves our out of sample error, especially when we have noise present. So let's talk about the very first type of penalized regression, which is called ridge regression. Now recall that in ordinary least square, we have the sum of squared error or the residual sum of squared given by this formula y minus the predicted y square of that. And we get the estimates or the betas by minimizing this particular cost function. Right? So betas are those values which minimizes this particular residual sum of squared. Now what we do in ridge regression is very, very similar to ordinary least square, except that now we want to put a constraint on the coefficients. So we have the residual sum squared as earlier. We want to minimize this. However, we have a additional constraint here which says that the sum of squared of the coefficients have to be less than a number t, where t is usually a small number. Now, those who have gone through Lagrange's multiplier and so on, you will see that this is no different than adding another shrinkage penalty to the very first equation. So we multiply the Lagrange multiplier lambda here and then add this particular term into the cost function and then try to minimize the betas with the new cost function, and that will give us the new estimates of the beta coefficients. So essentially we have a constraint here. Lagrange multiplier can be multiplied into that, and then that gives us the new cost function. So the cost function in ridge regression becomes the original cost function plus we are adding this lambda times the new penalty that we have added here. Now lambda is a complexity parameter and it controls the amount of shrinkage. This is a hyperparameter for our model. Um, Adding this particular term into our cost function has the effect of shrinking the estimated beta coefficients towards zero. Such a constraint will improve our fit because shrinking these coefficients have reduced their overall variance. We use similar kind of techniques in other places as well. For example, in neural networks, we also penalize the overall cost function by adding sum of squared of parameters there, that is known as weight decay. So how do we do the parameter estimations here? So for ordinary least square, we know we have the residual sum of squared, which is given by this particular formula, y minus the predicted y, which is beta naught plus beta 1 x1 plus and so on, square of this whole term. Now we can write this in matrix form as summation of y minus x beta transpose y minus x beta. Okay, the solution for this, those betas which will minimize this particular cost function, is given by x transpose x inverse x transpose y. In ridge regression, it's very similar. So we can write the cost function as y minus x beta transpose y minus x beta, plus we are adding this extra term lambda beta square, which can be written as lambda into beta transpose beta. Solving for this equation, we can see that the beta parameters for the ridge regression will be given by x transpose x plus lambda times I, where I is the identity matrix, inverse of that whole thing multiplied by X transpose into Y. So this gives me my parameters. Now, as we can see, with this X transpose X, we have added a non-zero term onto this particular matrix, and then it gives away, it reduces those cases of singularity because we have added a non-zero term here. Um, Now, how does this lead to shrinkage of the coefficients? So let's try to understand that a little bit. So as we said, our beta coefficients for ridge regression will be given by beta equal to X transpose X plus lambda I inverse X transpose Y. Multiplying X on both sides, we will get this particular equation. Now, if you do an SVD decomposition, singular value decomposition of our matrix X, the data matrix, um, which could be written as UDV transpose, where D is the diagonal matrix. If we put all of those values instead of X, that value comes out to be UD D square plus lambda I inverse into D U transpose Y. So V gets cancelled everywhere. Now this one, if you want to write it down in our non-matrix form, we can write it as sigma uj dj square by dj square plus lambda into uj transpose y, where uj's are the eigenvectors of, or the column vectors of the matrix U, and D are the diagonal elements of the SVD matrix, the diagonal matrix that we get. So as we can see, the beta ridge kind of reduces or shrinks the coefficient uj transpose y, which would have been the original coefficient for our OLS. That is multiplied by this particular term, d square by d square plus lambda. And since lambda is positive, this will be smaller, less than 1, and hence it kind of shrinks the overall, the coefficients, original coefficients. So what ridge regression does is it adds a positive constant to the diagonal X transpose X before inversion. So it gets rid of singularity, any of that if it's there for the data set. It also shrinks the coordinates of y with respect to u by this factor d square by d square plus lambda, and the greater shrinkage is applied to those coordinates where d is smaller, right? So lambda with respect to d will be larger and the shrinkage will be smaller there. And those are those eigenvectors or those directions which have smaller variance. So essentially what this penalty is trying to do is reduce those coefficients in the principal component direction where the variance is very, very small. So that's another way of looking at it as to how ridge regression tries to shrink the parameters and which parameters are getting shrunk. So this shrinkage parameter lambda, if it is equal to 0, then it's the same as our ordinary least square estimates, right? So it has no effect on the ridge regression. As we increase lambda, the coefficients will shrink more and more towards 0, and with lambda being very, very big, all of the coefficients will become very small or 0, and essentially it will give us a null model. So here is a diagram which shows these as lambda is increased, all of the coefficients of different variables shrink towards 0. So selecting a good value of lambda is very, very critical for our estimation of the regression parameters or the betas themselves. Generally, cross validation is used to select this lambda because it is a hyperparameter and there is no other way to get that. Also important to note is that the ridge regression coefficients estimates can change substantially when multiplying with the given predictor by a constant, because we have this penalty factor. So if you multiply the coefficients, let's say by a, that gets into the penalty factor and lambda increases. Hence, it is best to apply ridge regression after standardizing all of the predictors. As shown here, we can come up with new predictors, which is the standardized form of our original predictors. Before solving the estimates using ridge regression. All right, so let's talk about bias and variance trade-off. As we know, mean squared error is bias plus variance. Now, OLS or ordinary least square estimates, these generally have a low bias, but they can be highly variable, especially when our total number of data points is close to the total number of features which are given. However, in ridge regression, when we add the penalty term, it makes the estimates a little bit biased, but it also reduces the variance substantially, hence reducing the overall mean squared error as well. So as we can see in this diagram, as lambda increases, as the penalty increases, the variance will go down. After a point in time, the bias will increase. However, the overall mean squared error will initially increase and then, initially decrease and then start increasing. So we want to choose a lambda where the mean squared error is the smallest, and not in the training set, but in the test data set. So that is how we choose this lambda. As we have already talked about, increasing lambda will increase the bias but decrease the overall variance. So some of the advantages of ridge regression, one is the computation is simple. As we said, it has a closed form solution. So for any given value of lambda, which we can estimate using cross validation, we plug it in and then we can calculate or estimate the beta values. Also, there is no singularity. So ridge regression can be used even where a number of features is much, much larger than the number of data points. This is a situation where ordinary least square will completely fail because the ordinary least square equation will not have a unique solution. The overall matrix will have a rank which is lower than the data matrix. However, ridge regression will still give us a unique solution in such cases. So these are some of the advantages of ridge regression. However, ridge regression also has certain challenges. The penalty term will never force the coefficients to be exactly zero. It will only shrink them. So we will always have the model with all of these p predictors. So if p is very large, let's say 5,000 or so, it will create a challenge in our model interpretation. An alternative for this is the lasso technique. It's another technique of penalizing the coefficients. Lasso stands for least absolute shrinkage and selection operator. So Lasso works in a similar way to ridge regression, except in Lasso, we have the L1 penalty. And I'll just explain what that means. So our cost function here is the same residual sum of squared, but here we are adding the the sum of the modulus of the coefficients themselves, and this is known as L1 penalty, and L2 is the squared of the coefficients. So this gives us this particular equation. Now the constraint here in Lasso is essentially that the sum of the modulus of all the coefficients or betas is less than equal to some number s, where s is a small number, is what we usually choose. Now L1 penalty term here, it will shrink the coefficients, some of those coefficients exactly equal to 0. So Lasso performs a variable or a feature selection because those coefficients which become 0 have no bearing on the final prediction. Now this equation, the Lasso, does not have a closed form solution, so the parameters are estimated using quadratic programming. And lambda, as in the case of ridge, it is chosen using cross validation here in Lasso as well. All right, so we talked about Lasso again. Lasso also has certain challenges. Lasso will not work very well when we have multiple variables which are collinear with each other. What Lasso does in case of multicollinearity is it will randomly choose one of those multicollinear variables without giving any importance to the context or the domain in itself. Which means it will eliminate maybe the relevant independent variable and choose something which is completely irrelevant. So one alternative of Lasso is the ElasticNet. In ElasticNet, we combine the characteristics of both Lasso and Ridge. So it reduces the impact of different features, as in it shrinks the coefficients, but it also doesn't eliminate all the features completely. So in ElasticNet, what we do is we add both the L1 as well as the L2 penalty terms into our cost function, or residual sum of squared, and this is our new cost function, and our new estimates of beta will be given by those which reduces the overall cost function of this one. So ElasticNet formula is essentially we are adding Ridge plus Lasso. It's kind of adding all of the three. Now let's compare all of the three different techniques. So in when we add L1 norm, what happens is, let's say we have two parameters, theta 1 and theta 2, or beta 1 and beta 2. The residual sum of squared, which is the a squared term, essentially has these kind of ellipses where we are looking at the beta parameters. The L1 norm creates a curve like this, right? So it's a rhombus where the value of theta 1 plus theta 2, or modulus of theta 1 plus theta 2, will be equal at all of these edges. So essentially, the solution that we get is where this edge touches this particular oval, and this is the solution. And we can see this particular oval will not touch this line anywhere except for these axes itself, and hence it will reduce this coefficient completely to zero, whereas keeping this coefficient. In case of ridge, what will happen is the penalty term is also an oval or a circle. So what we are doing here is, the solution will be where uh, one of the coefficients given by root mean squared touches the coefficient given by the squared of the coefficients themselves. So these will touch here and not on the axis itself. And that is why it will shrink the factors but never make them zero. In case of elastic net, it's kind of a compromise. So this is not a straight line. It's also not a circle or an oval. It's some kind of a shape like this. And hence it will try to shrink the coefficients further, closer and closer to the axis. But it will not exactly be zero as well here. So it keeps all the features, never make them zero, but still tries to reduce or shrink the coefficients themselves. So as we see, the Lasso will produce simpler and more interpretable models. It will completely get rid of many of the features. Lasso can also generate more accurate prediction than ridge regressions, okay, and which is very, very interesting, and we'll see this in an example. ElasticNet will reduce the impact of different features, but will not completely eliminate all of the features. And with all these three, the tuning parameter lambda is selected using cross validation. Now in ElasticNet, remember that we have two different hyperparameters. In all of these, as we increase the value of lambda, the variance decreases and the bias overall increases. All right, so now let's get into a demo, and I'll show you in Python how we can build these different penalized regressions, Lasso, Ridge, and ElasticNet. Um, so I'll stop sharing and then I'll share back again. So here, as we can see, we'll usually import our pandas, numpy, and matplotlib. Now, what I'm trying to do here is show you the effect of all of these penalized regression, but with a synthetic data set. So I'll generate a synthetic data set from sklearn.datasets using make regression function. So I create a synthetic data set with 4 features, total 20 samples, and I add a little bit of noise. So my X will have 4 different features. I convert that into a data frame, And here is how this data frame looks like. So I have 4 different features, 20 rows of data. Now what I do is I also create 4 different random variables, and I'll add them again to that particular data set. So I use the random dot numpy's random dot uniform function, uh, and these are between -1 and 1, and again I add 20 of those. So here is the very first random variable. This is how it looks like. Now I append all of the 4 into my x underscore new variable, and my new data frame of x looks like this, right? So I have added these 4 different random variables as well. Now let's look at the correlation first and see if there is any kind of correlation on this. So I'll use the Seaborn library for this. I create the correlation matrix and then I just plot them as a heat map. And here, as I can see, the diagonal is essentially those variables themselves. So the correlation is 1. But other than that, all of the correlation usually are very, very small, negative 0.03 to maybe positive 0.03, nothing stronger than that. So I do not have multicollinearity in here. Now I'll also try to plot the scatter plots of y versus each of the columns in x and see how does it look like. So the first 4 are the ones that I got from the function make underscore regression. As we can see, there seems to be some kind of a relationship here. And the next 4 are the random variables. So this one, I don't see any kind of a pattern between y and x. So these seem to be completely random. Now what we'll do is we have these regression functions, linear regression, lasso, ridge, and ElasticNet. All of them are part of linear model in scikit-learn. So I import all of these and then I create each of these model. In ridge and lasso, I have this hyperparameter called alpha. So I'll initially put alpha equal to 1.0. For ElasticNet, we have 2 hyperparameters, alpha and L1 ratio. So I'll keep alpha as 1 and L1 ratio as 0.5 for the time being. To train the model, we just call dot fit and provide the data x and y, and that does the trick. Now what I do is just collate all of the coefficients in one data frame so that it is easier for me to look at. So linear, ridge, lasso, and ElasticNet, the coefficients are given by the LR model dot coefficient underscore and so on. I just collated all of them into one data frame and then I can look at the table. So here, as we can see, the linear regression gives us these coefficients. We have the first 4, but the other 4 variables also feature in the random variables which have come in, right? With the ridge regression, it has shrunk the coefficients as compared to this one, so they are smaller. But it has also added these other 4 random variables. Lasso does a pretty good job. It doesn't shrink the coefficients that much, a little bit. However, it understood that the other 4 variables are completely random and it has made those coefficients equal to 0. So it has selected the right variables here. ElasticNet again tries to shrink the coefficients. However, it doesn't make these 0. It still continues to have these. And the penalty here is not as high as the ridge regression. It's half of that. So these coefficients are a little bit higher as compared to the ridge regression. Now we can try with different alphas here. So for ridge, let's say, I change the alpha value to 0.1. For ElasticNet also, again, I change the alpha value to 0.1 and my L1 ratio to 0.8. So I'm now giving a higher weightage to L1 penalty and lower weightage to L2 penalty. Again, I train the model calling the fit function. And then I again collate all of these coefficients. Remember that I haven't changed the coefficients for linear regression and ridge. I have changed it only for linear regression and lasso. I have changed it only for ridge and ElasticNet. So now if I look at this particular table, linear remains the same. Ridge now changes. So now here we can see that the coefficients are shrunk, but not that much, quite close to the linear regression ones. And these, the four random variables there, the coefficients have shrunken much more. As you can see, here it was minus 3.2. This has reduced to minus 0.07. For ElasticNet as well, our coefficients have shrunk. The random variable coefficients have shrunk as compared to the previous one. Right now, if you want to get to the optimum value of lambda, we can do this for ElasticNet. As an example, there is this new function called ElasticNet CV. It uses cross validation to get to the optimum value of each of these hyperparameters. So here I'll do that. I'll call ElasticNet cross validation. I'll do cross validation, a 5-fold cross validation, and I'll give the random state as 0 initially, and then I again train the ElasticNet CV model with this, and then print the best alpha value as well as the model coefficients. So after doing this, the best alpha value comes out to be 0.23, and these are the coefficients that are corresponding to the best alpha here. So that is how we can get the best alpha. Now, how much does the coefficient shrink in Lasso? Let's try to look at that, right? So if we put Lasso at 0.01 and then try to run this, we'll see these coefficients, 0, 0. One of them is still not 0. If we make this alpha as 1 and then run it again, we'll see that it has shrunk all of the 4 random variables. So that is good. Now what happens if we, let's say, increase it to 100? Then we'll see that it has shrunk some other variables as well. It has only kept one variable here. Now what happens if we increase it to even further? Let's say we make alpha equal to 1000. So the penalty for the coefficients are increasing. In this case, all we get is a null model, right? So there are no model coefficients. We have just all zeros for all of the coefficients. So that is all here. I hope this was helpful for you. Let me go back into my previous screen again, and I'll cover a few other things here. So we looked at this particular demo. Now here are a few references if you want to go and read further. This is a classic, an introduction to statistical learning with applications by Trevor Hastie and Robert Tibshirani. Robert Tibshirani and Trevor Hastie were the ones who came up with the Lasso formulation itself. So they are both professors in Stanford. The other book that they have written is Statistical Learning with Sparsity. It covers the Lasso as well as some other generalized linear models. Both of these are available online completely for free. So you can go and download the PDF versions of this book and read it. There are a few other books, Learning from Data, a short course by Y. Abu Mustafa, and Machine Learning, a Probabilistic Perspective by K. Murphy. You can buy them on Amazon and read through this. So with this, I hope this was all helpful. Again, I am Sachin from Accelerate AI. You can look for us on YouTube by searching Accelerate AI, or check us out on LinkedIn with Accelerate AI. If you have any queries, you can write us to us on acceleratedatascience@gmail.com, or let us know in the comments here. Again, thank you so much for listening. I hope this was helpful.